Did you enjoy? I didn't even leave the beach up, huh? That's how bad this is. Oh my goodness. There we go. Oh, look at that. Bahamas. Nice. But let's get back to reality. Reality is Wishart is ruining our mojo on Friday before spring break, before St. Patrick's Day, before everything, right? Let's think about this here. Some of the questions you have are good, very good. But it's hard to plot the density across a line of variables because the problem with that, I mentioned, even for the smallest covariance matrix, you've got a four-dimensional graph to show. However, there is a way that I can trick this to show it to you. I should have done this before, but as I'm walking back from the break, I'm like, I should do this. So let's try this real quick. Let's look at the code. In the MCMC Pack library, there is the ability to generate random numbers from an inverse Wishart. The I wish function. I wish. That's what it's called. I kid you not. I wish. I wish too. What I did was I created this right here. This was actually a correlation matrix I gave. Right there. This is this is variances. Right here. And this is the values of the priors the books say. Basically, it's taking these numbers such that they allow us to have like this prior that's very diffuse. But if I go and load the MCMC Pack library, I'm going to go and create, just randomly sample, let's say 1,000 covariances matrices from this I wish function. So what am I talking about? Our I wish is a random covariance matrix. When you actually use it, oops, no, that's not what I want. I need to look at my screen. Come on, Templin. What am I doing? All right, this is a random covariance matrix from this, from our I wish. There we go. So what do you do? What does it give you? For every time that you call our I wish, it gives you back a covariance matrix that has the dimensions of the matrix you give it. That's the psi matrix. And this is the new parameter, the number of quote, degrees of freedom. What we can then do is save the values of it. I'm just doing it sloppily, quickly here. The other thing I want to do is create a correlation matrix out of the covariance matrix. So if I did solve diag sim covmat. So basically I can take the matrix product this right here should give me a vector, a matrix of 1 over the diagonal in the covariance matrix. And if I pre and post multiply the covariance matrix by that, I get a correlation matrix. That's what I'm trying to do. So this thing right here. Now, again, I'm actually just I'm just gluing the objects together because I'm not being elegant in my code, but this will go a little bit slower, but it gets the point across. So let's let this thing run. Takes a little bit of time, but now let's take a look at the density of each of these, a couple of the variances and covariances to see what the prior is doing. So what I did was I simulated 1,000 covariance matrices from the inverse Wishart. We can go and look at the distribution of these things from those 1,000. So if I did, I need my plot back here. Where'd my plot go? Oh man. View, panes. Show all panes. Show plots. Where are they? There. Okay. I start to freak out. And it's like I got to recover, you know?
Are you going to repost what you're doing?
Yes, I will.
Commit it or whatever.
I'm going to commit it, all right. So here's the value of of the covariances. Maybe I can do a histogram. There's some really big, this is the first variance of the value. The first variable's variance. It's really, really big. Let's do, there we go. There's a histogram. No, let's do this. Okay, so we have a pile of values that are really small, but that's what we would expect for a covariance, this type of covariance, because it's bounded. But then it could be very, and it's not very likely it's very big, but just one thing at a chance, it drew a very big one, big number for us. And actually, if I did, there's our density between, those are values of what the variance might likely be. This is a variable. When you have a bounded variable, there's a formula for what the variance actually is. You can go and calculate what that is. This is sort of in the range. But you see, what this is saying is, these are simulate. I'm trying to kind of show what the prior distribution is doing through simulation. So I probably could run the simulation longer. But this line is an approximation to how the density works for it. So it's putting more weight on the lower end of the variance, but not a whole lot more. And that was for the first variance. Let's take a look at the covariance, which is this one right here. This is the first covariance right there. Or if I looked at the correlation, the first, this is the correlation between items 1 and 2. So here's the correlation. I'm doing something wrong with my core save because these values are, you can't have a correlation that's 10.
No.
What have I done wrong? Yeah, I'm totally screwing this up. Well, forget the correlation. Why am I doing that wrong? This is why I shouldn't do this on the fly. Yeah, I don't know what I'm doing wrong. I gotta go figure this out. No, wait, I do know what I'm doing wrong. I didn't take the standard deviation. You have to, the correlation is a covariance divided by the product of the standard deviations of the variables.
That would do it.
Mm-hmm. $50 for more warnings. Uh-oh. We had some not a numbers. Let's try one more time. I know that it's still going to have that same thing, but if I do the core save, I'm having, is it numerical stability that's my problem? If I see a density that's like a 2 here, that's a problem. Let's do 0 to 1. There. Anyway, this is what it's telling me the simulated correlations look like between, for the very first variable, -1 to 1. Let's try that. So we're starting to see peaks that are actually highly correlated, which is a little weird. If I made this 10,000, it's probably going to take too long. We'll try it one more time and try to smooth this out a little bit.
Do you have a 1,000 in the first one?
I had 1,000, yeah. So, long story short, really hard to pick inverse Wishards. One of the good things about inverse Wishards, why it shows up all the time, is because it returns a matrix that's supposed to be positive definite. Right, there's a lot of ways in Bayes when you're doing a multivariate normal. I could teach probably a whole 3-week sequence on ways of generating a covariance matrix with positive definite numbers in Bayes. But inverse Wishard is simple because it gives you this positive definite value. If you don't have a positive definite value, then that iteration of the chain you can't easily go and get a likelihood for. Yeah, I probably should have just killed this. Questions on inverse Wishard?
So what did you pick when you did for your Bayes?
I was following, I believe, where I saw it in the book, which was the variance of each item. What did I do there? been the variance of each item is effectively it. I grabbed the variance for each item, I multiplied that by the number of items, but then I divided by the number of items. So there we go. Now let's take a look at this. Yeah, so what this is doing is putting lots of prior weight on the off diagonal, at least in this small example. But let's just recognize this is a problem. Let's estimate the model as it is. We can play with priors if we want to play around to make things happen.
Quick question. Wouldn't it be and you can tell me to go to sit in the corner and just don't talk anymore. But wouldn't it be counterintuitive that you put in a lot of weight on the off diagonals? Because that is what, if I'm following what we said to be zero, so I will expect to don't have that.
That's right. Yeah, it is. I thought we were not. There's something wrong here that's not. Something's going on, and I'm not sure what it is. And so it is. I wasn't expecting this result right here. And it could be the case that maybe we're pushing the top. So when you start to see correlations of -1 or +1, there may be something about the way that the tolerance. This might be a numerical precision issue, because that's the other part with it, right? We're sort of having to divide by these variances, and if we've got issues with the variances, we may end up seeing that they're, apart from the 1, there's a little bit more weight on the correlations here, but that 1 is just so discrepant. The value is close to 1, which makes me think something else is going on with this function, which may not be going on in JAGs, or I don't have enough information to tell you. But as an example, though, what you should learn from this is, number 1, don't do examples with Wishart on the fly, inverse Wishart on the fly. That's bad. When you teach your Bayes class, don't do that. But second, don't do as I did there. Learn from my mistakes. Second, it's really hard to pick an inverse Wishart distribution.
But I think that is a great lesson, yes, because it really makes us aware of you can really do the analysis without checking these things.
Oh yeah, that's exactly it.
So I personally appreciate that you do it in the fly.
No.
Because it really makes us to think about, you can just do it blindly.
That's right. Yeah, it would be tough to do it blindly. But look at this, the correlation. So, okay, so there's something weird about the correlation. Speaking of that, there's something weird about the correlation. This is the correlation between items 1 and 2, and this is the correlation, the density of what we drew for the correlation with 1 and 3. So with that, these are looking the same. Like it's like the same shape of them across, but we have something's going on that's causing this. To see not a number show up because of what I'm doing with basically with the correlation matrix, and to have this happen makes me think I've got.
Sounds maybe going to infinity.
That's exact, and that's where I think this would start to show up. So anyway.
So starting on line 476, the low data until this. What is R and what is K?
So R in this case is our the psi matrix that was on Wikipedia, and K is the new parameter, the number of degrees. In this case, variables. So R I picked to be the variances themselves. So this is the variances of all my variables.
So R is a matrix that's diagonal?
It's a diagonal matrix, so let's just do this.
Where the things on the diagonal are the variances of your variables?
That's right. That's what I was trying to pick it to do, but I think I did something where
Because I see that you fed it into the Wishart, or D-wish.
Yeah, so there's a couple other things. Hang on a second. Let me get there, all right? So this right here is a diagonal matrix. Okay. So what I'm giving it is the variance is divided by the number of items is my diagonal, which I thought I was following something in the book for that, but I may be wrong. And then what K is the number of items itself. So this diag function right here takes this vector of variances and makes it into a matrix. That's all that's doing. So I could play around with that, but let's just leave that for right now for a second. Let me try let's just go through this real quick. So if Wishart, if in univariate land for the variance inverse gamma is the conjugate prior, then in multivariate land for the covariance matrix inverse Wishart, right? So here's the catch in JAGs. In univariate land, it wasn't the variance we were having to plug in. We had to plug in 1 over the variance. And in multivariate land, 1 over the variance is really the inverse covariance matrix. So instead of the inverse Wishart, we are using
uninverse Wishart?
the Wishart. The Wishart distribution. Similarly, though, the parameters are phrased the same, so you can still keep that in place. Here we go and grab, so let me just run through the parameters for themselves. You will need to understand this command because even though we're doing this for data itself, when you run a factor model with more than one factor, you'll have a covariance matrix. That covariance matrix will be attached to a multivariate normal, so we'll use a similar approach to estimating covariances in that as a general feature. So if we're doing like a CFA model with 2 factors, which we're about to do in just a little bit, that inverse Wishart will show up to the factor side as a prior. Okay? That's why this is important. Whenever you have a psychometric model with continuous latent variables and more than one of them, more often than not, it's multivariate normal, and that's where Wishart shows up.
Or a mixed effects model with more than one random effect.
That's right. You've got an intercept slope. There it is. So let's define this. This is using, we're going to go and do this a little bit differently than you've seen before. The JAGs model syntax to define the model likelihood or the data likelihood itself based on the model. We're going to take the vector of observations for each person, right? So I have a given person, and then these are all the observations. I have 1 through I. And we're going to say that follows a multivariate normal distribution. So this is different from the univariate case in that this is dm norm, right, instead of d norm. We give it our prior mean. We give it our prior, this is now an inverse covariance matrix. So for our mean parameters, we're going to say that the prior mean was 0, the prior variance was 1,000,000. So what I ended up doing with all this syntax right here is we have a mean vector with a bunch of zeros, and we have a mean precision that's 1 over that. It's a diagonal matrix. Okay. And then we have to put priors on. So the parameters, these parameters of our model are mu and sigma inverse. That's what it's going to estimate, and it's going to estimate the matrix now, right? I'm going to save all of those. So mu is dm norm. That's a mu, the means, have a multivariate normal distribution with the mean vector of zeros, and that prior mean precision inverse sigma of the mean matrix is inverse precision. And then here's the big one. Sigma inverse follows a Wishart distribution. Right, so this is sigma inverse specified, where we have R and K as its parameters. R being our attempt to give us a covariance matrix, K being our number of variables in this case. And then for every step of the chain, I go and convert the inverse covariance matrix. I take the inverse covariance matrix and I invert it to get back to the covariance matrix. Because I want to save the covariance matrix. I don't care about the inverse covariances. Make me irrationally angry. I think that's the polite way of saying they piss me off. Really make me mad, right?
Yeah, this is like job security stuff right here. Like this is just unnecessary.
All right, so shall we let this thing fly and see what happens? There we go. It's initializing the model, and you'll note, if we look at our samplers, we have a conjugate Wishart and a generic, which means it's going to fly through this stuff, relatively speaking. Oh, I didn't save the parameter vector. Where are my parameters? do it right here. I'm saving mu, sigma, and the deviance. And draw, whoa, don't do that. Draw the sample, sort of flying. Anyway, I feel like we need some Bayes music when this plays.
This is flying? Like, are you flapping your wings? Is that?
It's just generating lots of, it's just floating like a bag in the air from like American Beauty. Just sampling all of our.
Wow, I thought it has a very called American Beauty in a long time.
Yeah, I'm old, that's why, yeah. Used to like that movie. If you haven't seen the movie American Beauty, you're probably younger than 40.
How many of you see them?
Okay. A long time ago I saw that. So let's take a look at, so that is our saturated model. Let's take a look at convergence, because convergence is the first step in the path to enlightenment. Nirvana? Nirvana. There we go. Ones. This is our Gelman-Rubin R. Our covariances are spectacular. Let's take a look at our values for them. These are the estimated values of variances and covariances. There's a lot, right? Because I have all of them, plus I have the estimated values, the mean, and I have a deviance as well. Now, we could do a similar type of thing with this. We could go and look at the posterior predictive model check with this model and our data and see how it should look, right? Sort of as an ideal. First, what we're going to do is I'm going to skip. I wanted to show you what happens if we skip the data simulation part, because that part's kind of weird too. Like for every step in this chain, we have a covariance. Why can't we just use that to compare to our data, right? So let me just pull that out real quick. And here, this is a simulation, or I actually grabbed that there. This is, whoops, figure margin's too large, which actually they're not, they're too small, right? This is, for each value of the covariance, this is the covariance between, this is each one of our covariances. So this is taking effectively the mean value of our covariances from our, so this is the point estimates. This is from our model, and this is actually from our data. This is plotting our mean covariances for what our model did, our saturated model, versus our mean covariances for what's in our data. And you'll note we're spot on, right? We make estimates of what the MLE should be pretty closely. So if you were to go calculate the relative bias, you're not going to find it with this one. So we do. Now let's compare the model implied covariance matrix. So this right here is what we got for every step of the chain. This is not a posterior predictive check. This is taking the covariance matrix for every step of the chain. This is the variance of item 1, right? So what am I saying? Each chain iteration has a covariance matrix. In cell 1,1 of that covariance matrix is the variance of item 1. This is the plot of all, this is the posterior distribution of the variance of item 1, right?
Where the ML is the mean of that thing?
That's right.
So you're still referring to it as a posterior.
This is a posterior distribution, right? So this is not a posterior predictive check, in that to make it a posterior predictive check, for every one of these, I would have had to grab a simulated data set and calculate the variance of it. So you can imagine where that might go a little awry. This right here is the density that this black line is from our saturated model. The red dashed line is from the CFA model we just did. But that's a variance, and we should be pretty close to a variance based on what the model is. Where we think it's a little more likely where it happens to be, but otherwise not too bad, right? This is the covariance between item 1 and 2 from our posterior distribution of our saturated model and of our CFA model.
Can you show some more variances?
Yeah, you want to see item 2?
Yeah.
Maybe. Crap, which one's item 2? Here, hold on.
I just want to see if it's the same tendency. Let's think we're more precise.
Let's do, that would be number 12. We need 12 here. That's item 12's variance in the saturated model, item 12's variance in the CFA model. But similar shape, just moved a little bit, right? Okay. You want to do another one, or are you good? I can do one more real quick. How about item 10? So what am I doing again? I'm plotting the posterior distribution of the model implied variance for item 10 now, and the model the model implied variance from our CFA model for item 10.
So that's a wiki top.
Yeah, it is. It probably. I see that, and I think either we probably run a longer chain. It's smooth. We just didn't sample enough in the right places, and it's usually where I do. But you're going to see some messiness in the plots themselves. It just happens. All right, now let's go and so that was just comparing model output for posteriors. Let's do the posterior predictive check. Let's go and take a sample of our posterior, generate data, calculate the covariance matrix in each case, and compare them. Right? Because what do you think is going to happen to this when we use this to generate data? It's going to widen because data will have sampling error that we're going to throw in it, right? So, the data part, so this is an interesting part. This is why I'm showing you this, to make you think about the posterior predictive model checks. By throwing the data in there, we're fuzzying up the model fit. We're basically going to have, it's going to be much more variable for model fit, I think we're going to see. So, this is the posterior predictive model check for the saturated model. So in this saturated model posterior predictive model check, because I have the covariance matrix directly specified in the code, I grab it from the right columns and I plug it into my multivariate normal, and then I save the sample statistics I want. Now now let's compare. So now I've got a bunch of variables, right? For the saturated model, for the one we just ran with the Wishart, inverse Wishart BS, right? Let's take a look at what the chain thought the variance should be for a variable. Right, this is the posterior distribution versus what a posterior predictive check of that posterior distribution should be. All right, so what am I doing differently? One is just taking the parameters that came from the chain and plotting them. One is taking the parameters from the chain, generating a data set, calculating the covariance, and plotting those. So this is going to compare what happens by looking at the data themselves. So this is the plot of the posterior for item 1's variance from the chain. And this is the same thing from the sampling, from the posterior predictive check. So the difference between these two is the black line did not have the simulated data function. The red line took samples from the black line, simulated data, calculated the covariance. And you'll see the tails are thicker, and that's the sampling error that we see there.
So if we had more people, they'd match more?
It would be very close. That's right. All right. So
this is just all saturated, right?
All saturated right now. Same thing with covariance. This is the posterior distribution of item 1 and item 2's covariance. And that's the posterior predictive distribution. Right? So black line again, straight from the chain. Dashed red line came from the simulated data that came from the chain. Right?
And the uncertainty is being captured by having wider shoulders.
That's right, yeah. So the red line should be a little bit more spread out because this is effectively representing the sampling process. What I get stuck on in my head is the estimates themselves should already have that sampling effect already because of the whole Bayes, the model being tied to data, but there's also the influence of prior there. So I think that's what they're trying to replicate without it. So it's an odd thing. All right, now we're going to simulate. Let's just take a look at the posterior predictive model check. Now we're going to do the posterior predictive check between the CFA model we just did, the one with the one factor, and our saturated model. So here's this is the CFA model's implied variance from the CFA model posterior predictive variance, right? So CFA model parameters led to simulated data, led to variance. This is saturated model. So those distributions are pretty much right on top of each other. And this is where I was saying, so these are comparing the two posterior predictive distributions. This is the way I think the posterior predictive check should work. Rather than comparing this with a single line, you should be comparing two distributions. And one way you can do that, one really simple way, is to use a QQ plot. Right? I took the quantiles from the saturated model and lined up the quantiles from our covariance model, and if they are from the same distribution, you should see most of them fit the line. And sure enough, they do. There's you could do a Kolmogorov-Smirnov test. You get a value of divergence. I don't like the p-value is less informed, but the divergence, how much they diverge, is the bigger thing. This is looking at the cumulative distribution. Like this is sort of the biggest difference in cumulative distribution functions throughout.
So what does that number mean?
I don't know if it's rescaled, but you can think of it as, if you look at a cumulative, like the ogives, it's sort of the biggest distance that you would find from one line to the other across the span of from 0 to 1. And this might be rescaled to be on a different metric, but that's what I think of it as. It's been a while since I did this. All right, let's take a look at the same feature for item 1 and item 2 covariance. There's what the CFA model, posterior predictive distribution of the covariance, was. There's the saturated model's posterior predictive distribution of the covariance. So now, instead of comparing it to a line, we've got a distribution. I don't know, this doesn't look too terrible when they look side by side, right?
Well, this seems more fair in two respects than what the book did,
Mm-hmm.
right?
Mm-hmm.
Because you're doing it by simulating your data in both cases and because you don't have one answer.
Mm-hmm.
So it's like the line is different in two ways.
It is. The question would be, did I phrase the model appropriately? Should it have been a multivariate normal or whatnot? But since I'm in a class of CFA models, that's why I'm doing it this way. We could do the QQ plot. By the way, there's the reference line. No, that's not right. And the same thing, the model divergence was huge. Right, that number. So this is a way, I'm showing this to you again to get you thinking about Bayes concepts more than this. Don't do it this way yet. More study needs done. I'd actually like to start a research project on it if anyone wants to join me. But that's more to think about what we're trying to do in Bayes. The very first way, where we compared it with the point estimate from the data, is the way that's typically done. That's the way I advise if you're writing a paper right now until we have further evidence for changing. So now, yeah.
Is much written about goodness of fit indices from a Bayesian framework?
There's a lot, but the articles I've seen are very much like I just presented. Well, you could do it this way, and you could do it this way. There may be much more specific articles to different models, and that's probably where I'd have to go. I haven't read those, but I've looked at more of the general, kind of the big picture. The more famous articles that are out there are more, well, you could.
What I personally like is that push away from the cut score.
Yeah,
Yes.
I like that. Yeah, you get to see uncertainty with it.
Exactly.
Okay, what you can do alternatively, which I can't do to show you, did I save this file? And of course I forgot to save the output from it. You can go, the other thing you can do to compare models, so this is sort of comparing saturated versus CFA model. The other thing to do that's also really valuable is to create the DIC, right? Remember, the deviance information criterion is an information criteria, a criterion that allows you to make a decision about which model might fit the data better. In JAGs, there's a DIC samples function. Now you'll note, R2 JAGs automatically gives you the DIC, but the values aren't equivalent, and I can't replicate the R2 JAGs values with the same seed. So I'm not showing that. But this right here will take a long time to run, particularly for the saturated model. But it will give you a value of DIC. And if you were to have that value of DIC, you could make a direct model comparison between the CFA model we just fit and the saturated model. That's an easier number, right? So if you wanted to say, for model fit, you wanted to make the claim, which model fit better, my saturated model or my CFA model, we should see the DIC should be roughly the same between the two. What's roughly the same? That's a problem with the DIC. But if you see a big discrepancy between the values, it should imply that there's a big problem in model fit. What's a big discrepancy?
Could you do Bayes factor?
There are Bayes, so Bayes factor is another way of doing it. Bayes factor for some models can be created. So Bayes factor, what it's trying to do is come up with a model likelihood after integrating out the parameters of the model effectively. So now we have to talk about an integration function that goes across a lot of space if we really do it, unless we can go either with an approximate Bayes factor or otherwise. There are approximations to Bayes factor that are out there. I'm not sure they're very good. I haven't talked about it. The other part of, that's why I haven't talked about it, my motivation. The other part of Bayes factor that I haven't seen in a big sense is that Bayes factor, if you learn Bayes factor in like the basic Bayes, beginning Bayes, it's like, look at this distribution with one parameter versus look at this distribution with one parameter.
Yeah.
We have 300 and some odd parameters to integrate over. It's probably not going to give us a reasonable, I haven't seen a Bayes factor in use in a big model. I have seen people have come up with formulae to approximate a Bayes factor, but I don't trust those very much either. So, remember you taught, we had a colleague at Kansas who's very active in this and loved the Bayes factor, and I remember asking him, where's the big model example? I don't remember him saying he had one, so maybe I was wrong about that. I'm wrong a lot, but I haven't seen a whole lot of this in psychometrics.
So you do count the factor scores then, as the thing, as parameters?
Yeah, factor scores are parameters in this, yes. So anyway, if you wanted to do the R to JAGs to go and do this, you'd have to go down and you unhighlight, uncomment my code to make that work. Okay, questions? How many of you are overwhelmed?
I'm just whelmed right now.
That's good.
I'm going to be overwhelmed in like a half hour.
Underwhelmed? How many of you are underwhelmed? That's okay too, I won't take offense. How many of you are frustrated?
With my children or with cats?
I didn't specify. If you integrate across which reason and just give me your marginal level of frustration. Now I speak like a
Is a version of Omega for CFA at the Bayes framework?
Yeah, we could do that. Okay, so
Wouldn't you need an omega chain? Like,
so let me get to that. So let's talk about that. Omega. What is omega? And I haven't gotten to this very much because I don't want to start battles, but
Oh, I put my finger in a tension.
what is omega?
reliability if you add shit up.
Okay, reliability for adding up variables if they fit a factor model. Now that's a key, right? Reliability for adding up variables. Why are we adding up variables? We have a model. What the hell? We have a factor score.
So how will you go about a sense of reliability?
Let's do that.
Yeah.
Let's do that. By the way, I'm fitting a model, though, that doesn't fit the data. What's that?
You said it wrong.
Yeah, I did.
Raw!
Yeah, I was about to say.
Try to throw it stuff. It's like, reliability. I promise I won't throw anything at you. No, actually, we made a very good point. There's a couple of reasons I haven't talked about reliability here, and that's because number one, we have misfitting model. So any estimate of reliability we make is going to be an overestimate.
Yeah.
Right? Remember that. I don't think it doesn't get emphasized enough. Reliability that you calculate here is always an upper bound. It's contingent on model fit. Right? You don't see that, especially if you're in the testing industry. Right? Because what's model fit? Right?
People tend to always say it like, oh, it's a lower bound.
Yeah, well, it's upper bound in this case,
When
yeah.
the model doesn't fit,
Yeah.
for sure.
Yeah.
People always tend to play it in the other way. Like,
Yeah.
You know, if we don't meet that assumption, maybe the lower bound.
No, not so much. So reliability here, if you wanted to calculate a reliability, let's talk about the ways. Those of you who've taken, I think you teach omega here, right? So in your CFA class,
I don't know.
have you heard of a coefficient omega? Sometimes called Raykov's rho, I believe. Congeneric model reliability for a sum score, those things come up?
I don't think we covered it in class.
Okay, shall I cover it now?
Yes.
Okay.
Yeah.
You want this or no? Is this good or bad? This is going to be like a 15-minute divergence. We okay with
We're
that?
not gonna finish CFA today.
No, I will. Okay, maybe not. Do you want, I mean, it's okay to go slow through this. There's so much to it. Okay, so under CFA model, this is the thing that drives me nuts about the use of CFA. You use CFA, you show it fits, in that case it didn't, and then you add shit up, the ASU model.
ASU measurement model.
And you're like, oh, look, here's my score, ta-da! Right? It's kind of weird. So let's remember what we're doing. We have y, our CFA model, y for an item and person is equal to... Thank you. Okay. This again. Y for item and person is item intercept, and we'll just do this for a single factor, okay? Make it a little bit easier. Lambda for the item, factor for the person, error for the item and person, okay? Now, if you add this up, and for a person, bless you, if you wanted to say, what's the reliability for a sum score, then you would say, okay, what's a sum score? We'd say, well, let's do this. Sum of y, item person across I equals 1 to capital I items. And then we could distribute the sum, right? We could say this would be the sum of mu I across the space of I. And here, the sum lambda I f for the person across I plus the sum of E person I, right? Okay? So now, when we look at this, we have the sort of idea of what's what. If we break this down and we say reliability, rho, in our case is usually sigma squared for the true score over sigma squared for the data, total, right? Which another way of saying that is variance of true score over variance of true score plus variance of error, right? So now, in this sum score, we have to sort of denote what represents true score and what represents error. So in our case, this part right here could be thought of as the true score. And this part right here we thought of as error. Okay? With me so far? So now, what is the variance of true score? I'm going to derive like
Sum of lambda and then square.
Yeah, so the variance of true score is the variance of the sum of mu I plus the sum of lambda I fp. All right, and so here what you can see when you do this is that mu I is a constant, so that goes away, right? So what we're left with is now, if you think about it, the only thing random here in this case, if you think of random variables, although in Bayesian it's harder than that, is the factor itself, right? So what you would get is this sum of lambda I squared times the variance of the factor, right? Or the sum lambda squared times sigma squared f. So that's your variance of true score. What is your variance of error? Right, that variance of error is the variance of the sum of EIP. All right, well, each of these things, technically speaking, this is a covariance matrix, right? But let's imagine they're all independent. In our example, they're independent. When you have off-diagonal variances, then you have to count those as well, but this is this is going to be then the sum of psi squared I in our case. Off diagonals, you'll have plus the sum of 2 times what that happens to be. Okay? So now, if you're going to go with omega for the sum score, under this CFA model, you've got the variance of true score, which is the sum of lambda I squared times sigma squared f, over the variance of true score, sum lambda I squared, variance of f, plus the sum of psi squared I. Right there. And there you get your variance for lambda. Variance for the sum score. To make that clear. So do you want to calculate that in the chain? Because each one of those parameters is a chain value. So you can come up with a posterior distribution of the reliability. Shoot, you want to do that? Thanks, Ariel. Thanks. No, I'm just kidding. I want to do this. Do you want to do this? Does anyone want to do this?
I want factor score reliability too.
Well, that's easy, actually. Relatively easy. It is and it isn't. Depends on who you're talking about, what reliability is. Let's do this. Sorry, JAGS. Manual. I want to see if there's a sum function. There usually is sum. Observable. There it is. I could sum. Wonder if I could just. I just want to make this real quick here. Sum lambda equals sum of lambda. Sum psi equals sum of psi, and then omega, which is what Rod McDonald, one of my mentors, called this, though I've heard other people call it other things. This is sum lambda times sum lambda times, in our case, we have no, it's the sum of lambda all the way squared.
Is it that way?
Mm-hmm. Mm-hmm. I'm in the wrong model. I need to go here. This one. Here we have sum lambda times factor variance. Right? Divided by plus sum psi. Now, if we add omega to our list of variables to save, where are my parameters? Let's see if this works. Oh boy. Always the worst thing I can ever say. Let's see if this works in front of class on the fly. No! Line 39. What's my error? Sum lambda. It doesn't like the sum function, I think. Okay, watch this. I can just add them all together real quick. 3. Hang on here. 2, 3, 4, 5, 6, 7, 8, 9, 10.
Yeah, take that R.
That's right. And there probably is a way to shorten this in JAGS. It's just on the fly. I'm sorry. Not going to be able to give that to you. And the same thing is going to tell me about sum psi. Two, 3, 4, 5, 6, 7, 8, 9, 10. Oops. And now you see why I'm throwing pins at reliability. enraged, irrationally angry about nearly everything. What? What did I do now? Did I not rerun this? I thought I did. Oops. Nope. It's not doing what I need it to. Some lambda. Is there like an overrun for this?
Sure.
Oh well, I may not be able to make this work.
Sorry for that.
But
you can
You
take
have
it.
a quilt under it. You're supposed to have a quilt.
that's the end of the.
Yeah.
Oh no, I think it takes equals, right? So I'll do this and change this. All right. If anyone else sees an error, you get the point. You can sort of see a posterior distribution for this if you can make it work. Maybe I'll make it work over spring break. I'll spend my spring break for you, making it work. Spring break Lawrence summing up lambda. Try one more thing. Colon. Yep, still a problem.
But so conceptually, you don't like omega anyhow.
Right. I don't think it's. I think it's silly to add
Yes.
things up after you've done a model for
So
it.
how would you think about that? I think that
Good question.
will be. I don't know how to think about it.
Let's take a look at what we have. For each person, we have a factor. Right. So let's take a look at, just because it's easy to get to, person 177's factor score. So we can do so here is the posterior distribution of what we think this person's factor score should be. We think the point estimate of the posterior distribution is somewhere around -0.25. What's reliability? Reliability. If we go back to our reliability formula that we know and love, right here, right, is sigma squared for the true score over sigma squared total. But for our case, the factor score is what we need to make the reliability of, right? So if we think of what the factor score is, we need to figure out what is the reliability of the factor score that we would observe that's true. That's the true distribution reliability. Right? And so I would like to think of that as, what is the distribution of our factor score, right? Because if we had no error, then what we should see is everybody's distribution for if there was no error at all in our estimate of the person. What do I mean by no error? If we were spot on, we had infinite precision, this distribution would be very, very small, right? So what I'm making the case for is this is an index of error in our estimate, right? So here's our distribution of error, effectively. What's our distribution for true is what is our factor score variance. Let me go and find that in the column names here. Factor variance is column 2.
So you want the mall one and not the variance of the EAP estimates?
That's right.
Okay, because that's two different numbers. Right?
That's right. Well, the variance of EAP estimates is not from the model. So what am I saying there? If you went and got the actual variance of each of the factor scores, Like, or go.
Like if you come up with a mean factor
You,
score,
that's
you
right.
take that variance across those.
I don't want that one.
You don't want that one.
No, I want from model.
Okay.
Right? This is our point estimate for the variance of factor score. So if everybody had the right amount of variance, if we were to look at all the factor scores, right, we would say the variance in factor score should be somewhere around this amount. Right? So total variance, though, is sort of a little bit more difficult because we have to make a couple assumptions. Right? If our variance of factor score, it's easier to think about in a non-frequentist approach, but let's imagine our variance of factor score is 0.5, right? So here is F, right? The variance of factor score, let's imagine we have a normal distribution of factor scores, which we assume that we have, although the posterior may be a little different from normal. Then what we should see here is this variance is, let's say it's 0.5, right? Sigma squared F is 0.5. If we saw no error in a factor score, if we saw none, what we should see is that let's take a value of the factor score. Let's say this is -1 right here, right? This is 0 or something like that. Then what we should see is whenever a person has a factor score of -1, there's no standard error to it. It's just -1. The question then becomes, what is the variance of error? Or what is the total? Right? So what we end up having here is some type of a range around that factor score that we have to account for. So when we build things up, when we say that we're looking at sigma squared factor over sigma squared factor plus sigma squared error, we should see sort of the total range of what factor scores might be and how much that differs, right? So that if we look at the total, right, F plus E, this total range might be much wider, right? And that discrepancy between the two means that what we're seeing with the factor score reflects not just factor, but factor plus error, right? With it.
We have to assume everybody has the same amount of error around their factor scores to have a number that comes out of this.
We may. There are more complicated ways that we could do it too, right? So if we were to go and do that, what we could say is we could come up with the distribution of all the factor scores from all of our chain, right? We could come up with the total distribution itself. That should be able to do it, because we could calculate the variance of that thing and come up with total, right? If we wanted to. But where I'm after with this is that variance of factor score is a chain function, right? Whereas variance of error, all this stuff for factor scores comes from the chain. That's what I'm going for, all right? And the reality of variance, the way that we do reliability, is this very first plot of this person's factor score right here. An index of reliability is talking about how much variance we observe right here in this person's factor score versus how much variance we'd observe overall. But because factor scores may have different amounts of variation, although in our case, in our model, believe it or not, they all should have about the same variance. In the CFA model with complete data, there's one factor variance. It's not the same in other measurement models, but let me see if I can grab the summary of this. Okay, I wanted to go to the plot down here. What I wanted to show you was the posterior standard deviation of all these things. Here's our standard deviation of our posterior distribution. Take a look at the standard deviation of these factors. Now they wiggle a little bit, but that's, I believe, chain error. If we run the chain a long time, what you're going to see is most of these turn out to be right around the same, but 0.7, 0.8, 0.9, 0.17, 0.18, 0.19, those are the standard deviations we're talking about. In a CFA model, we get roughly the same. If we...
Yeah, and like in frequentist, it would be literally the same.
Mm-hmm.
What gets outputted next to the EAP.
Now, here's the part that's causing me pause to hesitate in a Bayesian sense, but actually makes it much more precise in the Bayesian sense. If I'm going to go and say that my total variance right here is this thing, this function right here, factor plus error, I'd have to make the assumption previously that factor and error are uncorrelated to make the sum of those things. Is that really what we have in our posterior, though? Why don't we find out? Right? I'm totally like way off script on this one.
But I'm sorry to take your office.
No, it's good though, right? You like?
Factor and error are correlated. I'm going to lose my mind.
You're gonna lose your mind.
That's like the definition of error.
Well, let's find out. Let's find out. Let's find out. Damn it. Okay. All right. So not a lot of correlation there, right? We want that's one person's factor score with the factor variance. There's another person's, right? So what we're seeing here is what I was going to say, which is this, if there's uncorrelated, we go and uncorrelate all of this, we should be able to say that if there's a constant factor variance, which we should have in a CFA if we ran the chain long enough, we could calculate a factor score reliability that would be based on the idea that the ratio of the factor score variance, the distribution of the factor, versus the distribution that we observe for people's factor scores themselves. Does that make sense? Kind of an odd idea. And if you really wanted to get like sort of technical about all that and actually calculate it based on the posterior altogether, we could take the distribution observed by lumping everybody, all the scores from our factors together, like putting them in one big vector and making a plot of that, getting the variance of that. That's the distribution of factor scores, right? There's a variance there. That's total variance of factor score, right? That's the denominator. Should I do that the next time? You want me to do that? Why don't I do that? Make some reliability, and we'll do CFA for another week. But you can do homework starting now. We have 5 minutes. I'll talk about this the next time in depth. In fact, I'll make some slides.
You already have slides on this.
I'll make better slides. And by slides, hand gestures and drawing. I don't know what it's become, but lately slides have like sapped my will to live more than anything else in my life. That sounds terrible, but like, oh, making slides. But no, it's fine. I'd like to make some slides. I'd like to try to make this clearer somehow, either through syntax or otherwise. Maybe its own file, an auxiliary file. I did want to show you a little bit about the two-factor model. I don't need to do this very, oh hell, you know what? No homework homework won't be due in 2 weeks. It'll be due April 5th. Don't start the homework yet, all right?
Is that 8 already?
Yeah, and see me, I'm not in town, so. We can make it the next week. All right? Is this helpful at all? Is this interesting? Do you want homework? You can try homework if you like. You don't have to. All right? Another gift for you on spring break.
You could have them try to fix your code.
And we just watch with popcorn.
Hey, Templin, what about this? Oh, I'll try that. I should have been like, no. You're out. All right. That's actually part of the fun thing. When you get to be like colleagues and sit around, because I have a great deal of respect for both of the people, actually all the people in this room, but especially my colleagues. And when they're like heckling me over here, it makes me want to try and show them something. And it's like, I'll prove it. And I screw up even more. Leave the ego out. Just be like, I don't know. I'm sorry.
So I'll give you a compliment. I love the fact that it's the code that's tripping you up. Like the sum function is stymieing you. When you can just derive shit off the top of your head from memory, right? That's impressive.
It's no memory. It's first principle.
But whatever. It's still
All right, everybody. I'm about to open my mouth and say unimportant things. So I'll just stop. Have a great spring break. Stay safe. Stay warm. Whatever. Don't think about class. We'll come back. We'll talk reliability and multiple factor models when we come back. Okay.